Here's sort of a classic warm-up problem for Newton's law types of problems, and it's pretty simple in the system here. It's a box here which is sitting on a frictionless surface, so it's on ice or something like that, and the box is being pulled, or potentially can be pulled to the right with some tension T. So that's all that's in the problem. That's the only thing about the object in the problem. And you're just asked a variety of questions here. The first question I'd like to know in this one right here is what would the tension be, so in part A here, if the box is at rest? And of course, rest implies V is equal to 0. So look at this and go, well, what would the tension be to keep the box at rest? And intuitively you might think, well, the tension would have to be 0. Because if this box is at rest and is going to stay at rest, there can't be anyone pulling on it or else it would start moving. Is that right? Well, I know that Newton's law says the x acceleration is the sum of the x forces divided by m. That's one of the useful forms of Newton's laws that we have. The reason why I chose the x-axis because it's all horizontal here. So if the velocity is going to stay 0, that means the acceleration on it must be 0 also. How do I know that? Because I know that v is equal to v0 plus a times delta t. So if I'm going to stay at rest, if this is going to stay 0, given that this is 0, the initial speed is 0, and I want it to stay at 0 for all times, then I cannot have an acceleration on it. So this is going to be 0. So indeed then, if I can solve this Newton's law equation for the sum of the forces in the x direction on it, that must be equal to 0. Now the only force on this in the x direction is the tension right there, so you can't conclude correctly that the tension must be 0 then if the velocity is going to stay at rest like that. How about part B? Part B asks something like the following here. What if the box moves at a steady 5 meters per second? A steady 5 meters per second. So from this, you have to read the words carefully. What does steady mean? Steady means it's at 5 meters per second and this number doesn't change. Well, what is this number? This number here is a velocity. So if this velocity, or it's a speed, however you like to think about it, if this speed doesn't change, if it's always going to be 5 meters per second, we're sort of back to the same problem here, where if the speed's not going to change, the a must be 0 once again. So this is the case here where you're at rest and wanted to stay at rest. Here's a case where you're moving at 5 and want to stay at 5. Either way, the x acceleration must be 0 in this case, and I can conclude once again that the tension on it must be 0. Someone cannot be pulling on that block if you want to maintain a constant speed, whether it's 0 or some other number. The last part of the problem says, what do you have to do if the box is going to be, part C here, so you can have a speed of 5 meters per second and an acceleration in the x direction of 5 meters per second squared. What would the tension have to be? So now you're in a situation where it does have some speed, and the speed will change because it does have an acceleration on it. So in this case here, I can fall back once again to Newton's law. A sub x is the sum of the x forces divided by m. I can fall back on that again and go, okay, look, a sub x is not 0 this time. It's going to be 5 meters per second. So I can put a 5 in for this, and then the sum of the x forces, well, the only force on the block, once again, is the tension. There aren't any other forces, so it's just a sum with one term in it. So it'll be the tension divided by the mass of the block, which in this particular case was given to be 50 kilograms. So the mass here is 50 kilograms. So if you want to know what that tension is going to be, you can solve this for the tension. That's the power of Newton's law. It generates equations for us that we can solve. It's going to be here 50 kilograms times 5. So I get a tension here, something like 250 newtons. That would be the tension required to maintain a 5 meters per second squared acceleration on the block. The velocity, turns out, has no bearing on what the tension must be. Now, obviously, this velocity is going to change now because I've been part of this acceleration on it, but that's the way the problem will go.